Hello and welcome to this video on understanding and mastering function selectors in Ethereum, and we'll actually also touch on Yule a little bit as well. So understanding function selectors is extremely important because it makes you a very robust developer. It ensures that you know how the code works, that it does what it intends to do, and it also plays into things like call data. You'll understand essentially where it's used when you're calling different functions, and it just makes you a better developer, a safer developer, and a more optimized developer as well. So I hope you're going to enjoy the deep dive. We're going to do a few things. We're going to look at kind of like a high-level overview of function selectors first. We're going to cover in depth how to compute them. And then we're also going to dive into some of the theory behind it and even get to the bytecode level to understand how it works at that level as well. And we'll show some Yule as well, actually, how it works there. So I'm super excited to get started, excited for you to be here. Please subscribe. Please click the like button if you like the content and you'd like more of this produced. So first, I just want to give a super high overview of a function call in Ethereum, just highlighting the components that are important to us now. So we imagine we're some user, noted here, and we want to call a smart contract, specifically a function in a smart contract that's deployed somewhere. Fine. We create our call data. We have a video on that where you can get to master API encoded call data. Once we've done that, or like as part of doing that rather, we need to pick the we need to actually compute the function selector. So we're going to get into how to do that, and we also need to then append the argument to that. That's not really the focus of today. That's more like in the API encoding videos we have. But the selector is something we need to compute. Now, okay, we send this to the contract. Okay, and I just want to note, normally this is kind of this side of it, like this stuff over here, creating the call data, computing the function selector, is what tools like MetaMask do for you, for example, like that. So it's not like something you have to do. And then, once it's done that, it basically sends, calls the contract. This contract here, again, this could be anything, Uniswap, Curve, whatever contract we're talking about. Now, inside this contract, at the bytecode level, behind the scenes, so to speak, this deployed code, that's where we have this concept of a dispatcher, okay? So a dispatcher is kind of like, imagine like essentially back in the day when you had to call a friend, like for the very old phone system, right? You had to call into a dispatcher, right? Because it couldn't just connect you directly to your friend. You had to go to dispatcher, and then the dispatcher picked up and you had to say, hey, I want to call, Carl on so-and-so street. And the dispatcher had to then actually take these plugs in this board and put the plug in the right place there, and then you got connected to the person you want to talk to. All right, that's how it used to be in the day. You had to actually kind of dispatch through who you wanted to be, or wanted to basically call. Now, for Solidity and calling function Solidity, it's the same thing. You have to essentially call the contract, and the contract says, okay, great. It's just that I don't know what you're trying to call because everything runs on a stack, right? And a stack it's not very smart, right? It doesn't know anything. It just runs things on a stack, right? Operations on a stack, and those are very low-level operations. So we need the concept of a dispatcher that can find which function you're trying to call, and that's what kind of this part is in the dispatcher. And this search is linear if you have 4 or less functions. So you have 1, 2, 3, 4. It's linear. You have 5 or more. It's going to be binary search because that's going to be more optimal. We're going to look at an actual example of binary search as well, which is going to be pretty exciting. Okay, now that we found the function behind the scenes, what Solidity does is, or like kind of what this EVM does essentially, is it prepares for this function call. So first you kind of enter this essentially a function preparation stage where we just take care of the input arguments, make sure that they get checked, make sure they get prepared, make sure the call frame is ready, things like that. And then we call the function, and we do the function logic, whatever that is, and then we handle so that's here, and then we handle the return values and so on, and return everything. If it's a uint, great. We make sure we put that into memory and everything, if it's return value and so on, and then everything gets returned back to the user essentially, or like the caller, in one way, shape, or form. So this is kind of the anatomy, this is kind of the flow of function call, and the important thing for us today is going to be around, how is the selector computed, but also how are function calls dispatched and how do we find this function now that we know the function selector. This is what I really want you to understand. That's my goal, is for you to walk away really being like, I get how this works, I get how the function selector works, how you compute the function selector, and how the EVM, using a very simple stack-based virtual machine, basically finds this function. All right, because it's not like the EVM has a concept of like, go find this function, right? It's not like there's an opcode that's like, go find this function. It's not like that. We have to construct this dispatcher from lower level function operations like addition and equality and comparison and all these kind of things. So we'll definitely dive into that. Now, with that background, how about we just jump into the first example here. So I'm over in Remix now, and I'm going to zoom in a little bit more. We're over in Remix now, and we're on example 1 here. This is all going to be made available, by the way, this code in my GitHub as well. Okay, so I'm going to link to that, and you'll be able to see all this code. So you don't have to you can just copy paste, do whatever you want. All right. So here's a selector example. We have 3 functions. We have foo, we have bar, we have bus. All right, and then we have some supportive functions here that all they do is just get the selector of those functions. Okay, so again, in a smart contract, you deploy it. There are functions in there, in this case 3 functions. If they are external public, they will have a function selector. Like, they'll have some sort of way to identify it, because others outside of the contract can, like, we need a way for them to identify within the contract what you're calling. Okay, now if it's an internal function, it does not have a function selector. Why? Because you don't need it. Like, it's internal to the code. We just know where it lives within the code. Okay, we don't need a way to identify it as if we're calling it from the outside. So foo has a function selector, but bar has a function selector. Bus does not have a function selector. So we're going to test this. We're going to deploy it. So let's go over here. We'll go here to deploy and run, and what we're going to do is just deploy this code as is in the just the Remix VM is fine. Good. So this deployed successfully. We can expand it down here, and we're going to call the various things. So first of all, we can call foo. Doesn't really return anything, as you can see. Doesn't do anything. But then we can call get selector foo, and this leverages a tool in Solidity that can actually kind of, I guess, short circuit a lot and make you do this a lot quicker. Which is, you can actually just call this.foo.selector, and that gives you the selector of the foo function. Okay, so you don't really need to compute it yourself. You can just do .selector. It's a member function of this function handle here. So we can call get selector foo. You see this? So this is C2985578. Okay, so what is this? The function selector, just a brief kind of intro to it, is really the hash of the function signature. So you have to take the catcheck 256 hash of the function signature. What is the function signature, you may ask? The function signature is this. Okay, so the function signature, so here's the steps. All right, so get the function signature. Okay, the function signature in this case is this. In general, if it takes an input parameters, like let's say it took a uint x or something, like this was the function name or whatever you want to call it in Solidity, well, now you have to convert it to a function signature. We remove the variable name, and we also remove any kind of like shortcuts for these type names, and we want to type them all out. So in this case, uint, we don't use uint, we use uint 256, and this would then be the function signature of that particular function that, again, we don't have here, but it was just an example. Okay, you can learn more about this in the documentation. Go to the Solidity documentation and search for selectors, like function selectors. It will tell you, they will tell you exactly how to map these types into what it should look like to be a function signature, which is this we're seeing here. And then from there, you know how to get the selector. Well, we know that. We just hash it. Okay, so you get the function signature, and then you hash it with catcheck 256. Okay. So you and that will give you some sort of, if you at least write it in hex, it'll give you some sort of thing that looks like this: OX, AB 1 2 4 blah 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 blah. I mean, there's not gonna be W's, but and write some number. I'm just gonna write some numbers, okay? And then da 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 da, and you're gonna get 32 bytes of this, okay? So it's gonna be a ton of these numbers, all right? And then you need to take the first 4 bytes of this, okay? That's how you, that is the function selector, the first 4 bytes of this. So then you do, now the question is, okay, if I have hex characters, what's a byte? I said first 4 bytes. So what's 1 byte in hex characters? Well, it turns out you need 2 hex characters to represent 1 byte. Okay, so you actually need, so this is 1 byte. Like I'm taking this up here now and I'm stripping off everything but the first 4 bytes to get the function selector. So this is 1 byte. Now I need the other byte, that's this byte. Okay, see, I'm just going up here. Now I need the other byte that's here. So I have 3 bytes now, and then this. Okay, so in this case, this would be the function selector. Okay, that's the function selector, and that's it. I'm done. I got the function selector. That's the process. Now, they do all that here. They all these steps, they just do here. They just do dot selector, and that's it. So here's method 1, which is very manual, and here's method 2, which is much easier. You just do dot selector. You just do whatever the function you have, function dot selector. So in this case, foo.selector, right? This dot foo.selector, okay? And you get the function selector, and that's it. And this will return the same thing. Okay, this will return the same thing, this thing, which is a bytes 4. You see, that's why we're returning a bytes 4 up here. You see? The selector, we know it's a bytes 4. It's 4 bytes. So that's what it is. Okay? Those are the 2 different methods. We are going to get into method 1 here a little bit. We're going to get more manual, increasingly manual now. All right? Because I want you to understand it at a lower and lower level until we can actually just compute it ourselves. Okay? But now you know. You at least have this available. This is probably the highest level version of getting it. Okay, so far so good. Get selector of bar might not surprise you. It's going to be very similar, but now there's going to be an argument. I mean, that's fine. It's just going to be this. Okay, so that's really it. Now let's just take a look at bus. Okay, so bus is actually an internal function. You'll notice right here, and I mentioned it doesn't have a function selector. So I wrote a function here to get that function selector, but it doesn't have it. So I actually expect an error here in this code, okay? All right, and we're getting an error. You see when we hover over here, it says member bus not found or not visible after argument dependent lookup in contract, okay? So the contract kind of behind the scenes, Remix kind of compiled it and it said, listen, I can't find the function bus in terms of it having a select or anything in the external public functions. And that's because the internal functions don't make it into that interface, right? Like they're not represented in terms of the functions. So it can't find the function is what it's saying. And that's because, again, it's internal. So there's no selector, okay? So that's it. So I'll comment that back out so we don't have an error. And that's it. That's like at a very high level. That's the easiest way to get a selector. Now, there's another way. What we can do now is actually kind of double check these numbers. So look out here. We had foo, this was function selector, and bar. Now I want to show you another way to do it. So you can go to this online tool here. So just search Kechak256 online. Like actually include the online word, just Kechak256 online. Search for that in Google and you'll find this pretty easily. Bookmark it, and then what we can do here is type in the function signature. If you type in the function signature, make sure you go to Kechak256. You'll see there are other variants over here. You want Kechak256. You type foo. Look at this. Look at what comes out here. That's the hex representation. I'm going to copy that over here. So for foo, we got this. You see? And then we could put an OX because it's hex, right? So that's a way to signal that this is the following characters, or hex characters. Anyway, so you see this was the whole thing we got. Again, we get 32 bytes just when we hash it. All this tool does is just hashing it. So you get everything. We need to take the first 4 bytes. We remember that is 8 hex characters. So we take 1 byte, 2 bytes, 3 bytes, 4 bytes. Sorry, 4 bytes, that's it. Okay, and you see by the highlight that they match all these characters. And that's it. So that's another way to do it quickly. Or if you just want to do it online, fine. Now I want to show you another way of getting the function selector. Okay, another way, well, let's go back here. We can go back to example 2. So in example 2, what we're going to do is go a little bit lower level. So instead of just calling the .selector member, we're going to actually just compute it ourselves, but using Solidity tools. So what I mean by that is we are going to, and you can see it here, we're basically taking some input function signature. Okay, again, this could be like the input could be like this. Okay. Oh, you see it down here. Okay. See there? There's foo and there's bar with some input. Okay, and so that's the input. It's a string. Now we hash it, and Solidity has this built-in function called Kechak256. So that's great. That's all we need. And then we need to cast that to a bytes 4. Now the Kechak256 will return a byte 32, and we're going to basically downcast that to a bytes 4. So we're essentially, by doing this, stripping away all the higher bytes. We're just taking the 4 bytes, and then we're returning that, and that's it. So you see this a little bit more manual because, you know, we're basically passing in the signature ourselves and using the built-in tools for that. So down here, when we call test selectors, after we deploy it in a minute, we're going to try it for 2 different selectors that we pre-computed. And we can see that we just did this in the online converter. We can do the same thing with this one. And we can see that it gives 0423, some blah, 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 and you can see that's the same here. Now, one thing just quickly before we do that example, I want to note too, I mentioned how, like, you don't include variable names like this. For example, this could be, you know, address, something, whatever. You know, a few things. One is this, there's a difference between the function kind of name, you know, with its parameter, like with its arguments and so on, that you see in the IDE, that you see in Remix. You see the name, you see the parameters, just like here. This is how you'd see it in Remix, right? There's a difference between that and the signature. Okay, like this is not the signature. This is just kind of telling you the variables and the types and sometimes where they live as a memory or call data, whatever. You want to strip all that away and you just want to simplify it. And also remember, there's that type conversion. You want to check the docs for what the type should be, how it should be represented. What I mean is this uint is not the type you want to actually type out for the hashing. You want to type out uint256. There are a few other special cases where there's some other types as well. But anyway, so the way to do it is, the first thing you do is, like, you know, you delete the variable, but notice also that there's no space. Okay, a lot of folks are committing some errors because they leave a space here, and we know from hashing that the space, like just a single character change, can change the whole thing, the whole hash. That's kind of the point of it, is that there's this kind of chaotic behavior. So just a single small change will change everything you hash. Just look below. Look below right here. This is 866D8, yada yada. If I change a single character, aka change this, I remove this space. That's all I do. It was just empty space before. It's all it was. I'm just going to remove that. You see how it's very different. 4, 4, yada yada. It's a very different number. Okay, and then, you know, we're going to convert these types into what they need to be, and then this is essentially what it is for this function, and this is what it is for this function, 0423. All right, and that's what we have here, 0423. So just a note on how, but this is also in the documentation, but just be aware of that. Okay, now where were we? We're going to deploy this. Okay, and we're going to go to this function signature, and now we're going to call test selector. So if true is returned or we don't get an error, then we know that these 2 assertions ran through and they happened, and that means, in other words, this calculation, which is a slightly lower level calculation again than before, that it actually worked, right? And that's actually the way to do it. So we're going to click it, boom, and we get return true, no errors. That's how you can do it. That's another way to do it in Solidity. Okay, essentially syntactic sugar, essentially on top of this, the other way we did it. Now, I want to show you one more way to do it. We are going to go ahead and here, again, this repo I'm going to make available for you to see. But I'm actually going to do it with Python, just because why not? In Python, there are a few tools you can use. One is more low level than the other. So one, you can import, like you can install and import the SHA-3 package in Python. So if you're using a package manager, which I highly recommend, you know, let's say you have pip or something like that, just pip install SHA-3. You know, just double check the exact install command, but that's what I would guess. And then, you know, you have that, and then from that you import catcheck256, and then all you got to do is just say catcheck256 of some function signature. Just make sure it's encoded. That's just how it requires it. And then once it's done with the hashing, you just need to do this, essentially get the hex value of it. That's where we get that OX yada 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 for 32 bytes. And then, in other words, and then you just need to take the first 8 characters. So that's just kind of like how that would look if you use the SHA-3 library. So you can see this example, by the way. This is a function in Python, right? This is a function, and you can see that we compose a signature here, and then we just call get function selector, and we input that signature, and then that selector is returned, and the program prints, here's the signature, and here's the corresponding selector, okay? The other method we can use is ethutils. Ethutils is just kind of a nice wrapper around some more low-level, you know, Python libraries that just make some common Ethereum commands much easier to access, such as getting the function signature. So basically, for method 2, what we do is we call function signature to 4-byte selector. So in other words, I want to convert my function signature into the selector, and they even say the 4-byte selector, just to be even extra clear about it, I guess. So that's what we call here. Okay, so in this case, all we need to do is just give the function signature. We don't need to do this encoding. We don't need to do anything. We just give it the string. It accepts the string. And then after that, we just need to call .hex. Okay, so because it comes back in bytes, basically, so we just need to convert bytes to hex. And that's similar to this, but as you can see, even easier because so this actually does return just 4 bytes, by the way. This is a bytes object in Python, and it's just the 4 bytes. It's not the 32. That's why we don't need to do any slicing or anything like that. And then we just call it .hex, and that's it. You get the 4 bytes in hex representation. Okay, so anyway, just so you know, this is how you do it in Python. So you can like kind of cross-check all these methods, but they should all agree for sure. So, okay, now we have an understanding of how to get the function selector in Solidity using the kind of very abstracted method of .selector. We know how to get it using, catch 256 and a bytes 4 conversion. And we even know how to get it in Python. We know how to get it online, right? With this like catch 256 online. So we have many ways now to get the selector. So the process is get the right signature. That's important. You got to start from the right signature and then choose your tool, whatever you want, and then get the selector. Okay. Similar thing the compiler is doing behind the scenes. When you have a bunch of functions in your contract, it converts all those and also computes the function, and that's actually where it uses these tools. It computes the function selectors so that we later on know which function we want to call. Fantastic. Okay, so now let's actually jump into the next kind of phase here. So I want to show you also how you can call a general contract as long as you just get the right function selector get a function selector that matches that target contract. The same with your values. What I'm saying is, and we know this from API encoding, so it's not really so surprising, but let's say we have deployed some contract, some target contract. That's this one. Imagine this is deployed on chain. Okay, and some time passes, whatever, and it's deployed and it's all good, and it has this function set value and it takes a UN256. Fine, whatever. Now imagine we know that, someone tells us just the function, signature basically, or at least the name with the parameters of the function in this contract. The question is then kind of how can we call this function? Okay, from another contract, this contract, the caller contract. Okay, how can I call into the target contract, making sure I call the set value function with some uint? Okay, how can we do that? Well, there's a few ways, right? I'm going to first show you the most low-level way this time of doing it, or one of the most low-level ways of doing it, and then actually after that we're going to look at the more common way of doing that, which is the more abstracted or higher-level way of doing it, an easier way of doing it. But first, just to drill in the concept of this function selector and kind of what it does. In this case, we're being tasked with deploying a contract called the caller contract, and it needs a function called call set value, and that function needs to call the target contract on chain, and it needs specifically to call this function set value with some value. So how do we kind of manually do this, basically, right? Let's say we didn't know anything else about it, and we just wanted to do it in a low-level way. Maybe sometimes you are constrained. I can't think of an example right this second, but maybe sometimes you are constrained that this is just what you need to do. Well, this is how you do it. So it passes the string to the catch 256. It does the byte 4 slicing. Okay, so it just takes the first 4 bytes, and that gives us the selector. All right. Then we basically say API, and this is kind of like a Solidity built-in function as well under the API library. So we do API.encode with selector. So basically, in other words, what this means is, what does this mean? It's basically API encode the following data given that I already have the selector. Okay, so I already know the selector. So, but just take the rest of the stuff I give you, like these parameters, and just make sure it all gets API encoded together. We have that API encoding tutorial in another video that'll even tell you how to do that by hand. But here we can take a shortcut and we can say API encode with selector. We give the selector, well, we just computed that. That's the 4 bytes. We know what a selector is now. And then we give the value as well. And here we can just put our own value. So now we do target.call. So in other words, we call this target contract, which of course we just put the address of whatever, whatever address this is deployed at. And we make a low-level call command with essentially that function selector with the parameter, this UN parameter. Okay, so that's basically the example. So let's try to actually do that. So what we're going to do is we're going to deploy this specific one here, the caller contract. Well, first let's deploy the target, of course. So let's say, again, the target is deployed now. It lives somewhere. The value is 0, of course, because we haven't set it to anything yet, so it's just default. And a default for UN is just 0. So it's just 0, but it's at least deployed. So it lives there at this particular address. Okay, we can copy it here, and we can say it now lives at this address. Okay, that's the target. Now we want to call it. So let's actually deploy. And again, notice this is completely separate. We didn't deploy them at the same time. We just, some time passes, whatever, and we then deploy the call contract. Great. So to call, we can call any contract deployed on chain, but in this case, again, we want to do the target. So we're going to do the address of the target contract, and then we're going to, let's say, change the value to 2, and we click transact, and boom. So we actually used target, right? Like, again, you can put any address you want here, but of course it has to be consistent with this set value, or else if it has a fallback, that'll be called instead. So let's say another contract was deployed on chain that did not have a set value function, but we use that contract's address here. Okay, so we're calling a contract that does not have this function. So there's no matching on this function selector. It does not have a set value function. Well, we can still call it. We can certainly still call it with this data here. That's totally fine. But if it has a fallback function, it'll go to that fallback function because it does not match that set value function. If it doesn't have a fallback, well, I mean, like nothing happened. You just called it and that's it. But in this case, it does have a set value function, so it actually works. So it will actually call that set value function. Okay. Now we're going to actually call it here. Okay. So transact. Great. It came back successfully, you see. And now we're going to go up and check, well, did that actually change the value? And boom, we click. It did, right? It's 2 now. You see? It's 2 right here, and we basically put that address there. Let's go to the next example. So let's delete that. Now we want to show how message.signature behaves. So message.sig, like msg.sig, is a variable that comes along when you call a contract and a function within that contract. That message.sig is part of kind of like a special variable. And it gives you the selector of the like most recent, essentially public or external function you called. Okay, so like if you call into foo, and inside foo, I just want to know what is the signature of, essentially in this case, myself. Like what is my own signature? This is kind of a shortcut, even more abstracted shortcut than kind of having to do like this .foo.selector kind of thing. I can just do message.signature. Okay, and also message.signature does not change if I'm inside an internal function. Okay, so I'm going to show you how that works. So just so you know, it's a variable that's available and it gets that signature. In fact, selector, but message.sig. All right, so let's deploy this now. All right, so we're going to deploy this contract. We're going to expand it down here. We have this event in this case, okay, and it just emits the selector. And the selector is what sits in message.sig. This message.sig again is a variable that's available to us just from the environment. Okay, we don't need to pass it in; it's just there. Okay, and there are other few variables like that, globals and special variables. You can read about those in the documentation. But first off, the foo. Now, when we call foo, all it's going to do is just basically emit in a log message the selector. Okay, so we call foo, and we're going to expand this down here, and we're going to see. Here is actually where the log, you see here logs under logs, it's an array, first of all, the log. So if we emitted multiple things, it would keep appending to that array. And the first things emitted would be at the bottom because it kind of appends like that. So in this case, it said, hey, here's the topic, here's the event and so on, but here's the arguments. So particularly look at the argument. The argument is the function selector of, foo, okay? And again, we have many ways to confirm that. We can go to the online confirmer, like we can go here, for example, we can paste it here. Here we would do foo. And then we basically see that this is the same as like C2985. Just remember those, C2985, right? Now I want to show you another thing now that sometimes maybe you only have the function selector. You might be thinking, wait a minute, all we've done is kind of go from the function name and the function signature into the function selector, which is this weird hex like OXC2985 thing, right? 4 bytes, right? What if you only have the function selector? Is there a way to kind of go backwards to the function signature? In general, no, because of many reasons. Like, you can't go from like the hash of something to the pre-image, as it's called. Like, you can't go backwards, first of all. Second of all, there could be many clashes as well, so you're never guaranteed. Notice that we only took the first 4 bytes. We're going to talk about clashing in a second. My point is just after the first 4 bytes, you could have a lot of different functions that had the same first 4 bytes, but then different in the last 4 bytes, but they would have the same selector, right? So they would actually clash. And we'll see an example of that. But anyway, but there are some special cases, and it's actually there are a growing amount of special cases, and that you can kind of go look up. If you know the selector, what's the function name? Okay, there's actually a database that's being kept right here. This is called the, like you can get to it at 4byte.directory. It's called the Ethereum signature database. And you basically just put the selector. Now, you put the selector and you get this kind of table with rows. What does these rows mean? They actually mean clashes, okay, of the selector. So in this case, I put in, this was actually transfer, address, and UN 256. This has this selector, OXA905, blah, 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 which again, we got from hashing this. We got this. And a bunch of other stuff, right? Remember, the whole thing is 32 bytes, but that other stuff is not shown. Now, notice that all these other function names, however weird there are, actually there's another transfer here, you see, just with another argument list. See that? That also maps to this beginning, okay? They all map to that beginning. That's why they all show up under the same selector. So it's actually pretty easy, relatively easy to clash. You can actually mine for that clashing as well, like someone did that here. You see, like someone was just kept iterating on this non-seer, like this number, and they just kept going up and up and up and up until you clash with this function, like this same selector as transfer. Okay. So, but in this case, let's take our foo. This is our foo, and we're going to search for it, and there you go. Foo shows up. Nothing has clashed with that yet, or at least no one has submitted. Now, this is a database. This is not a database. This is a database where people basically submit these function selectors into, and they say what's the signature. Okay, so it's like just anyone can submit this, and it gets validated, and then they just kind of keep appending this database. It's a centralized database, but then other service, they also have an API service, so you can actually kind of look up in this database if you only know the selector. So notice this is kind of like decompiling, right? It's not compiling, it's decompiling, because like I know the selector. Now I want to go back to what was the function signature. And then I can actually get that. So that's just another way to kind of cross-check. It does have a lot of functions in there. So at least most of the normal ones, okay? If it gets more esoteric or kind of something you made and that's named a little bit more specific to your application, you might not find it in the database. You can still submit it, for it to be included. But so I hope that makes sense. Now, okay, so that was kind of the msg.sig up in foo. Now let's actually go to bar. So in bar, I want to show you a few things here. So first of all, we're going to emit into the event like what the selector of bar is. In this case, we're going to get this selector. We'll double check, but we'll get this selector. Then we're going to call foo in two different ways now. And this is important. So notice that foo is public. Okay, but there are two ways we can call it. We can call it this.foo. This.foo, when we call this dot something in Solidity, it's almost like, you can almost think of it mentally as like, it's as if you're calling back into yourself, like back into the contract itself from some external contract. Okay, it's almost like you're not really going to look up your own code, so to speak. It's almost like you leave yourself and then kind of like you call back into yourself. Okay, that's what kind of this.foo does. Okay, so the alternative way is just to call foo, not this.foo, but just foo. That will mean that, oh, okay, like I know it's part of myself. Like I know it's one of my own functions. So I don't need to like pretend like I'm calling into my own like kind of contract, if you will. It's almost like a server where it's like, oh, it's just my internal code. I don't need to like kind of like, essentially like call out and then call back in, right? Like it's all internal. So that's kind of the difference. Now, so what's the difference then is that this.foo, since it's kind of like it's leaving the contract and calling back into the contract, it will actually call foo, and in an external mode, right? In that sense, like becomes like an external call. And in that case, foo will have a function selector. Remember I said before, external publics, they do have a function selector. Internal, like internal code, does not, because it's like you just need to jump to that bytecode, that particular place in the bytecode where it is, and that's all good. But it's like if you call yourself outside, well, you need to figure out which function you're calling and so on. So that's why you need the selector. And you don't in internal mode, right? So there's kind of external mode, there's kind of internal mode. So in external mode, now we're going to get the function selector of foo, okay? Because it's like we're calling it. But if in internal mode, again, it's like we're just jumping internally to that section in the bytecode. We're not doing anything with the function selector. In this case, we're not going to get up here, when we call foo, we're not going to get the function selector of foo. We'll get it of bar. Because the function selector didn't change, because we're not kind of entering into a new external context. We're staying within our own kind of internal context. So that's a very important distinction. That can be tricky. Okay, so we're going to see now this example here. So we're going to call bar. So what we expect is we'll see the function selector for bar. That's this FEBB kind of thing. Then we'll see the function selector for foo. It's going to change over and be this C29 kind of thing. But then we're going to see the function selector a bar again, even though we're still calling foo. Okay, but it's just like this kind of internal mode. It's like, okay, so let's go call bar. So we call bar. We're going to expand this again, and we're going to go look in the logs section. So let's scroll down. Here's the logs section. We expect 3 items. That's what we see. We expect the bottom item to be the first item. Indeed, that is this FEBB thing, and that is foo. Okay, sorry, that is bar. That is bar. Then we go to the next call here, this.foo, and we're kind of external mode, and then that's why now we actually get this msg.sig from the foo log emitter. Then finally we're going to call foo internally, and we get actually the bar function selector. Okay, so that's tricky. That's a little subtle. You might expect, oh, I call foo, so msg.sig is this function selector. But you have to think about kind of how we got there. Well, this was like internal, so nothing changes in that message kind of variable when we call things internally. So that's why msg.sig stays the same. All right, so done with that now, we're going to go to the next example. And we have, this is where I want to show you, I told you I kind of want to show you the low-level way before of like kind of calling, like using the selector to call a function, and now I want to show you the more like kind of high-level way. All right, so we had this example here. Remember, we had this target contract we wanted to call. We had to call a contract, and we used this API encoded data that we kind of ourselves put together here, and we did that because we imagined someone told us, or we just looked it up online if it was a verified contract, that the function name was setValue. Okay, what people do more commonly is they say, well, if we know how this target contract looks, what we're going to do is just use an interface. This is actually what interfaces are used for. You might have seen this before, right? There's a special command here in Solidity called interface. And what you typically do is then you put a capital I to indicate its interface in front of the contract name, which is target contract. So by looking up, again, maybe it's a verified contract, someone told us, we know the interface. And when you create an interface, you just need to essentially outline these external and public functions. Notice that, of course, there's no code here in the interface. It just tells you what these functions are, right? And that's all we need to do to call it, right? We just need the interface. So this is way more common. And then in this case, you can either define in your caller contract this interface variable here and fix the address because you already know it, or if you want to leave it a little bit more general, you can do this. And then notice how you can just wrap that interface around that address and basically say whatever lives at that address, well, it's a contract that does this, that has these functions, right? And then we can just do, like, now it's nice because now we can just treat it as if it's some, like, our own contract pretty much, or like a contract we know, right? Because now we just do .setValue, you see, .setValue. So now it's like we're just calling this function directly, you see, .setValue, and we just pass in the value. That's all we need to do because we have that interface. We've told Solidity, well, we've told the EVM in a sense, like, hey, I know this is my neighbor, this is my friend, I know this contract, I know what functions there are, so just pretend like we had this up here, essentially, right? Pretend like we just wrote that and deployed it. So we know there's a setValue function on there because I just told you here. Okay, so the interface just makes it a lot easier and nicer as well. You can see this is a lot nicer to read than the other more low-level method, which is kind of we need to do all this stuff. But that's kind of what it does behind the scenes anyway. Okay, so that is how that works. Now what we're going to do is, so we're over the message sake. Now we're going to look at the collision. We talked about the collision before. So the selectors, again, they can collide. It's not actually that difficult because there's only 4 bytes. Colliding 2 4-byte things together, like the first 4 bytes of something, is actually pretty easy. So here I have an example where I have this function called collate propagate storage. Why? I don't know. Imagine some application that has that. And it takes a byte 16 input. Okay? I don't care about the application, but that's what it is. And that has this selector. OX429, yada. Okay? Now imagine the same contract. I wanted to include, a burn function that takes some UN256 with an amount. Now I'm going to uncomment this. And look at that. When I uncomment that, everything just blows up. Let's see what the error is. So when I hover over, it says, there is a type error. There's a function signature hash collision for burn, it says. All right. So it basically says that, so in other words, the compiler doesn't allow clashes, which is good because that would be very confusing, right, for the compiler. It wouldn't, Like the EVM wouldn't know which function to call if they clashed in their selectors, because we need to give the selector when we call the function. But if they're two functions with the same selector, it's like, which one do you want to call? And it's not really smart enough to kind of infer, oh, it's a byte 16 versus a UN, right? Because in the ABI encoded data, there's no really difference between that. They look the same essentially, right? So, then we just can't clash, but that's a good thing, I mean, in other words, that just means that whatever you've deployed, I mean, you've never had a clash, yourself, unless you've seen this error, in which case, well, you just need to rename a function. That's really it. There's no other way around it. So in this case, if we just rename this to burn, I mean, it could be some like burn amount or something like that, whatever makes sense. So now they don't clash anymore, right? So it's also easy to unclash, right, once you've clashed. Or you just call it burn underscore or something like that, whatever makes sense in your application. But here it definitely clashes. Okay, so that certainly can happen. And that's also what we saw in the signature database, right? The first example I showed you, multiple rows in that database that map to the same selector. So that's just the clashing, not uncommon, not crazy. Now, finding the full 32 bytes, right, would be the equivalent of mining for the private key of an Ethereum account, right? That is not possible. I mean, that is practically impossible. But the 4 bytes, pretty easy to mine. Okay, so we're kind of done with this. So the last thing I want to do now is get a little bit deeper to the EVM level now. So we kind of know how to compute it. We know something about collisions. We know something about these helper variables that is made available to us. But what happens behind the scenes? Well, let's dive in. So what actually happens when when you call a contract and you call that function is that an EVM is spun up, right? On that client machine, right? You're calling this contract, you're calling this function. Your call goes to the node that's running the Ethereum blockchain, and basically the client will then start to decipher your call, and it'll start to say, oh, they're calling it with this selector with these parameters and so on. The EVM spins up, and the EVM again is just a stack of like very simple operations. It's not clever. It's not like the EVM has an opcode that says, go find this function, and like it just retrieves that function immediately. It doesn't have an opcode like that. We need to put together how that works, and that's kind of what we covered in the beginning. So we need to basically create, like EVM at a low level, the dispatcher. We need to create the logic for find the function. When I say we, I just mean more like it's not done by the EVM. Who does it? The compiler does it. Okay, the compiler does it. So when we write this code here, with different functions, foo, bar, bas, all this stuff, and we compile the code, the compiler makes sure to turn all this into the dispatcher, to the kind of the function staging area where it kind of prepares all the parameters, and then it actually calls the function, and then it returns the parameters from the function. All that stuff is done by the compiler. We also don't need to do that, at least in Solidity. In Yule, it's a little bit different. We'll see an example. But, in Solidity, we have to, or the compiler does all that for us. So a few questions now. If this compiler does that, what's the order that it dispatches in? And how does it search? I said here that the dispatcher looks for the function, but how? Like, there's no one to ask. It can't call anyone, right? So how does it do that? Well, it does a linear search. If there's 4 or less functions in the contract, it does a linear search. If there's 5 or more, it does a binary search. So it searches in different ways. And here I have an example. This is just a basic example. So if you go to evm.codes and you can click the playground up here, you get into this EVM playground, and you can actually run that code, and you can then get the bytecode over here to the right. And that bytecode includes the construction, like the construction of the contract, so the constructor segment, and then it also includes like the runtime code. And we're like in the runtime code now, and I have kind of scrolled down. You see here to the 41 in hex, but 41 like kind of bytes into the code. And this is actually the section where, because it's doing a bunch of stuff before this. Again, there's the constructor, there's a few checks and whatnot, but the dispatcher comes early on and comes here. So the dispatcher, what it does is, and again, the compiler has created this for us, but you see that there's nothing like go fetch me function foo here, right? Because this is just a stack. The EVM is just a silly stack that doesn't do much, but it does things. This is basic operations, and we can put together these basic operations to form more complex operations. That's exactly what this is. There's a function dispatcher. Okay, so now, how do you dispatch? Well, you load the call data. The call data has the selector, and it has the arguments. So it has the selector in there. But we need to extract the selector from the call data. How do we do that? Well, we know it's the first 4 bytes. So that's what this is about. It does a shift right, So it actually, what this means is like essentially shift right all your bytes, like all the call data, until there's only the 4 bytes remaining. Okay, so this essentially carves away everything else but the function selector. Then it does some comparisons. So you see here it pushes 4 bytes, these 4 bytes, and it does a comparison. Is it equal, yes or no? If it's equal, then jump 51, like in hex, but 51 hex bytes into the code from the runtime, from where the runtime code starts. Okay, so this doesn't mean jump here, 51. This 51 includes the constructor part. When I scroll up, it includes the constructor part. You need to start from the runtime code starts and then do a hex addition, basically, of where that starting point is, and then 51 down. Okay, and then that's where it starts. And of course, it has to be at some jump destination. Okay, so we can do that math now as well. But the point is, here is where we're going to load the incoming. We're going to get the selector of the incoming data. We're going to start comparing it, and you can see here that the logic is push the compiler knew, like the compiler created this selector, by the way, right, of get, of increment, decrement, and it put it into the deployed code. So this is kind of hard coded into the deployed code on chain. Okay, this function selector of the function in the contract. So now we're going to start to say, did you call this? Did you want to call this function? Yes or no? If yes, great, then jump to this location. If no, we'll keep going. Did you call this function selector? Yes, you did. Great. Then go here. What are these here's? Well, these things is where then that kind of function preparation segment happened, and then it goes to actually call the function itself, like the body of the function. That's what happens there. So this is like saying yes, and then you jump to where that happens. You need to jump out of this dispatcher, right? Because you can't just put it right after you. I mean, they could, but it's better to just say, just handle all this. Like first figure out which function it is, then you can always jump out of it till the end to figure to do the function logic, okay? But if not, you see it kind of just continues, go to the next one. Is this the one we called? Yes, then jump here. No, it's not. Okay, is this the one we called? And it'll just keep going linearly, you see? It just goes linearly through. So if we called this function, by the way, that had this selector down here, it would be a little bit annoying if this is a function we're going to call a lot. Why? Because we're going to spend a lot of gas going through this every single time. Did you call this? No. Did you call this? No. Did you call this? No. Did you call this? Yes. Right? Imagine we call it again, like a second later. Did you call this? No, so on, right? And so we're going to spend a lot of gas, technically, right? It would be better if this function was the most called function. It'd be actually better if this was at the top here, right? But this brings us into like the ordering, right? Let's talk a little bit about that. So this, I was saying these selectors over here, what do they map to, right? What do they map to over here, right? Is it in order? Like if I put get, increment, decrement like this, does that just map over here? Like to, get, increment, decrement, right? Does that happen? Oh, and we have count as well, right? Because it's public functions, so we have count too, technically, right? That would be the first one. Any public variable like that, they get their own functions. That's why we have more than 3. But so does it just map like that, or how does it map? No, so the answer is it actually orders it kind of alphabetically, essentially, but in terms of numerically, I should say. So it basically puts like 0.6 is like less than 3.7 is less than 6D is less than B3, right? So it orders it numerically, like hex numerically, like this, right? And so it just goes from the small to large. So if decrement, although it's the last function here, for some reason had this selector, like let's say it had that, well, it would go first. So it goes last over here to the left. The order, of course, doesn't matter over to the left so much, right? Like when you code it up, but still, if you just mentally think it's going to go in that order, no. Decrement right over there might be last. It might be first here. So if you don't call decrement ever, it's going to be a little bit annoying that it's first because, then we're not really going to get a gas saving or anything like that. Can you influence the order of these functions? No, you cannot. There's no way to really change that. I mean, yes, you can change the name. You can do some sort of like, you can do like decrement 1, 2. You can mine for a particular number here, try all kinds of numbers until the hash, like until the selector, is the smallest of all these existing selectors. So you can imagine creating a program where you basically appended all kinds of numbers and then checked against like basically the lowest value, this one, and basically said stop when it's lower than this, right? And then boom, it would be called first. Okay? But there's no way you can manually change that. So that's one thing. But now notice that's a linear search, right? Again, it does this, checks this, and so on. If I told you when there's 5 or more, it is a binary search. So I have another example over here where I just created like another count variable called count2 because that's not, well, it's not super creative, but it's just what I was thinking of in the moment. And then I duplicated these other functions, just appended a 2. So get 2, increment 2, decrement 2. Point is, now we certainly have more than 4 functions. Okay. In this case, now we actually have a binary search. So if you've never seen this before, it's pretty cool. This is a binary search. So, I mean, I think you've seen a binary search before, but maybe not in this context. So now, notice this. Let's just before we can get a little bit more overview of this. What I'm going to do now is we're going to look at the binary search dispatcher. All right. So again, this is kind of like a dispatcher. It arrives. And then it needs to be dispatched. It needs to be sent somewhere, this call data, right? Which function did you call? So we have this contract. I replicated it here, this kind of get to, all this kind of stuff, and screenshotted this as well from the playground. First, just show you the list of functions and their selectors. This is actually in this contract now. We have this many functions. We have 8 functions, and these are the names. And you can see they're not in order of what the IDE told us. They're in the order, again, of what is from lowest to highest in terms of numerically here, in terms of their hashes. Okay, or the first 4 bytes there. Okay, so that's how they're ordered, and this just happened to be the ordering. Okay, and again, if we had to linearly go through this and do a linear search through this, what would we do? Let's say we called get to. What would the EVM do? Well, it would do check this. Did we call that? No, we didn't. Did we call that? No, we didn't. Did we call that? No, we didn't. And so on. It would keep going until it hit that. Did we call that? Yes, we did. And then we call it. And by the way, if it doesn't find any of these functions, let's say we call it with some selector, we just make up anything. It's, of course, it's going to go through the list of its functions and say, hey, did I call this? Did I call this? Did I call this? If it doesn't find it, it's going to go to the fallback if there is one. Okay? Or it's just going to return do nothing if there is none. Okay? So that's what a linear search would do. And you can kind of start to see, like, if you had 100 functions, that would be a lot to go through in a linear search, right? So we have the binary search. That's the whole point of this. So in the binary search, here, again, it's the replicated code from the playground we just saw. But now you see this greater than thing suddenly pop in. We didn't see that before in the linear search. Well, that is because it's comparing. Are you less than or greater than? Now we're starting to see some sort of essentially cutting the problem in half kind of thing. So how do you do a binary search? Well, we have this list of functions. The way you do a binary search just in general, now we have an even number, okay? So like there's no kind of middle element. Like nothing that divides the list such that there's an equal number of elements on each side of it, right? For example, if we take this as the middle element, there is 3 items before and there's 4 items after. If we take this, it's kind of opposite. The way Solidity does it, or the compiler does it, again, this can change the future right now, is that it takes the higher of the 2, okay? So it kind of split this decision. So out of these 2, it just picks this as the middle element and calls this the middle. But you see, this is the first element now that we consider. We don't go to the top like we did for linear search and just kind of start at the top and go down the list. We start at the middle element. And again, this is what we call a middle when there's an equal number of elements. All right. So now we have the middle element. And you can see this is exactly what's happening here early on. We're actually going to push the middle element, and that's, of course, the compiler has stored that ahead of time in its binary search setup and all this stuff, right? That, it's not something it's finding live. This is already the deployed code, right? So, but now we're going to compare, or now we're going to say, is the function selector, incoming function selector, greater than this, which is the middle element of the list, of the list of our functions? If it's greater than, yes, great, then jump ahead to the right side of the tree, so to speak. If not, well, then, are you equal to that, to the root of the, again, this is the root of the tree, actually, right? This is the root of the tree. If you're not greater than, well, are you equal to? That's what this does. If you're equal, great, then jump down to where the function is. If not, well, then, split kind of like, depending on whether you're greater than or less than, jump to the right side of the tree, the left side of the tree, and then keep asking the same question for half the problem. So I'm going to show you now. So what it does is basically, we can draw this tree, is essentially we have this root, right? This is just the root because it's the middle element of that list, okay? Whatever is the middle element will become the root. So that's what we first ask. Did you call this function? So you can see if you kind of want to gas optimize in a binary search, you kind of want it to be in the middle, right? You want to optimize it not to be first. You want to optimize it to be in the middle of the list. Then you will get called first because then this is the first thing it checks, okay? So and again, that's if you have more than 4 functions. Now, if you are greater than, if the incoming function selector is greater than this one, it's going to go to the right side of the tree. The right side of the tree are these functions. They live there. So, for example, if you call get to, it'll first say, did you call get? And we're like, nope, we did not call get. Okay, great. Well, then we need to go to the right side of the tree. Okay, what's in the middle of the right side of the tree? Well, now we're talking about these 3 elements. Now it's easy to see the middle because that's this element, right? There's an equal number of elements on each side, so it's an odd number of elements. Anyway, now we get this. Great. So if we go to the right side of the tree, okay, think about it like that. now we have this as the middle element. And it will basically say, well, did you call decrement? That's going to be the next comparison. So notice, again, linear search would do this, it would do this, it would do this, it would do this, just go from top to bottom. Now we actually started with this. Then we went here. Again, I'm assuming we call it get2. Now what does it do? Well, now it's going to split. This is going to be the top node of this sublist here, right? Notice how it kind of split the problem in two as well. That's why it's very efficient. We're never going to check these functions. We're never going to check them. So that's very efficient. We're not going to waste gas on checking any of them because we know it's bigger than this. And that's what makes it very efficient. Was it this function? No, it was not. Okay, great. Let's keep going. So now we're going to split this side of the tree into what's greater than. Well, basically, we're going to keep going to the right here. And we're going to say, now, like, you know, for this sublist, create the tree. Well, there's only one element in this sublist, so it doesn't really, it just becomes the final node. It becomes the leaf, right? So in this case, we have B08. Cool. There it is. And that's it. Again, there's nothing to the left or right. So we just compare to that. And if it's not that, then we go to the fallback if there is one. Or we just, again, stop the program. If it is that, then great, we found it. If it's now up here, we said if it was greater than this, right, it would go over here. If it's less than, then it goes to the left side of that sublist. So that's this element. Okay. And again, this is just kind of general binary search. Like you can look this algorithm up anywhere. This is nothing specific to Solidity. Like this algorithm I'm showing you now, just if you feel a little rusty on the algorithm, this is not Solidity specific, so you can just learn that from a lot of tools online. But anyway, so this was the right side of the tree. Okay, so this is if our incoming function selector is bigger than this value, it'll start going down this side of the tree. If it was less than, you guessed it, it'll do the exact same thing, but opposite. Like it's going to be less than. So now let's pretend the value was less. Well, it's going to cut this second half. But now, again, this half has an even number of values, but we know what it does. We actually put the larger of the two in the center. These two elements jointly split the list kind of as middle element candidates at least. Well, it's always going to pick the larger one. So here we go. That's the larger one. We know the left side of the tree is then going to contain these two elements, which are going to be split again. This one is going to be to the right. So it's going to look like this. This is going to split down here, right? Because this is larger than that one. And boom, that's going to be the right side. So if we called decrement 2, for example, the path would be check, did you call this function in the middle? No, you did not. But what you did call, because it's decrement 2, is smaller than this middle element. Okay, it's smaller than, great. Well, then go down the left side of the tree. Fantastic. Now you call decrement 2. Is that larger than this current element? Yes, it is. Great. Then go to the right, and boom, there's decrement 2. So in just like 3 comparisons, essentially, you know, you compare to this, compare to this, compare to this, you reached it. Instead of doing 1, 2, 3, 4 comparisons. Okay, and it gets even better, of course, with like something like get2, for example. Right? Let's do that one. Get2, that's this that we're calling this. Get2, did you call this? Nope. But whatever you are calling is greater than this. I don't care what it is. I just know it's greater. That's all I know. Okay, it's greater. Great. Then go over here. Is what you're calling greater? Yeah, it's greater than this too. Great. Again, I don't know what it is, but I know it's greater. Fantastic. Go here. Is it this? Yeah, it's this. So that's 3 comparisons to call get2, the very last element of the list. What would a linear search do? You guessed it. All 8 comparisons. That's a lot. So we went from 8 to 3. That's a big savings, right? In gas and in time. So, okay, but we didn't quite finish over here. So now we have this side of the tree, right? C0, that's the root of that. Now we go again. And this also has an even number of elements, this left side. Like, again, they all become subtrees. It's a recursive formula, right? So now this subtree has 2 elements. That's an even number again, but we know which one becomes the root. It's the bigger of the 2, right? So this becomes the root. Great. And of that subtree, there's nothing below it. Again, all this other bold stuff, this down here is not valid. This has all been handled. These are the parents, or like, you know, parents and kind of cousins and all this kind of stuff. So this doesn't, so in other words, what I'm trying to say is there's no right side of that root here. It doesn't have a right element, which is fine. It doesn't need to have one. But there's a left one, which is exactly this one. Okay, so we're going to put that, here. And maybe I represent these final. Okay, so here, yeah, there you go. Okay, so there you go. That's the list. These are all the. This is how the binary search will look. These are all the elements. So you see that actually the most expensive function to call now is count, because you're going to need to do this comparison, this, right? So in general, you definitely want to avoid having these like very long paths. Like you want to split as much as possible. You want to kind of even out this tree as much as possible, because or else you're just back to linear search, right? But still, this is. I mean, you know, in linear search that would take 1 comparison. That'd be very optimal. but in binary search, it takes 1, 2, 3, 4. So binary search is worse in that case if you call count. But the runtime comparisons is more on average, and then binary tree is way better. Like binary search is way better in general when you're kind of equalizing over these functions in terms of many times you're expecting to call them. Okay. So, so that's the tree, and you're going to note that if we added in a lot more functions here, they'll just kind of get added as leaves here in this tree, right? And notice it's called binary tree because all these roots, they have two children, right? They have a left child, a right child. The right is larger than itself, the left is smaller than itself, and it just keeps going like that. Okay. Yeah. So that's it. So that's how the binary search works, and that's exactly what Solidity gives. Right? It does this comparison, are you greater than? And just in detail, just to make sure we completely get it, in that code I showed you, the line 41 is saying push this middle element of all my function selectors, am I greater or not, right? So this is the first comparison in the binary search when we compare to the middle element. It's comparing the input selector with the get function, so the middle element. If the input is greater than this, it jumps to 5b. Otherwise, it continues to the next instruction. When I say jumps to 5b, we have to be a little careful. It's not 5b. It's like by 5b bytes into where the runtime code starts. Okay, so don't go look at 5b and be like, oh, 5b, see, there's no 5b here. You see that? There's a 5.7 and a 5c, but it doesn't jump to 5b. It jumps like 5b, like bytes from the start of the runtime code, all right, into the code. Okay, but anyway, then it does, yeah. So if it's greater than this middle element, it compares it to the middle element itself because it could also be equal to. Okay, in which case we found it and we're done. But it also ends up comparing to all these other elements. That's just to say that those are these elements in the tree. And then, if it's less than or equal to, then it compares to the other side of the tree, left side of the tree. Okay, so that's how the binary search works. But in Yule, what's special here, we talked a little bit about, the function selector in terms of where it's located in the EVM. Remember, we couldn't change the order. It was like numerically ordered, and then there was that binary search. So even then, we can't manually change the order. When we code in Yule, which again is kind of like its own programming language, right? It's not just some version of Solidity. It's like its own thing. But Yule is the thing you open up in the assembly block in Solidity. Then you can code in Yule. But if we just were to write in Yule purely, we can still write smart contracts and deploy them and everything. In this case, we actually can change the order, because in Yule, we actually have to kind of write our own selector. That's very bare metal, Yule is, right, compared to Solidity that has a lot of helpers. So here we can get the selector of whoever is calling it. Now that is a function we've written ourselves below here. I'll cover that in a second, but just imagine we get that selector, we extract those first 4 bytes. Then we actually just do a switch here. We just do, was this the function selector, right? We just do case this. Was this the one? Nope. Was it this? Was it this? And so on. So here we can just put the exact order we want, because we can just make the comparison. You see here? We can just compare with this first. We don't have to start here. In fact, you see how this 6D is larger than the 3.7. So we can put in whatever order we want, whatever we think will be called most, which might in some applications be obvious. So in that case, we can do the ordering ourselves, and we have way more control of it. So I just wanted to highlight that's kind of how it looks in Yule. Now, this selector down here, the idea of that, and there's some more comments here if you want to read through it, but the idea here is that the way we just kind of implement it is like an integer division, essentially. So we divide out everything that's larger than the first 4 bytes, and then it kind of just gets cut off, essentially, is the main effect. And we're just left with the selector, which is the first 4 bytes. That's one way to implement it. You can also do a byte shift and all this kind of stuff as well. But that's just one way to do it. But yeah, so imagine, so in this case, we actually kind of had to write the dispatcher. The whole thing is the dispatcher was gets the selector, then makes the comparison. But the key is we can actually put the order we want, which can then actually lead to much more gas efficient contracts as well. So just wanted to highlight that. That's the example of how you would do the selector in Yule. I hope you got a much more kind of in-depth view into how the function selector works, how you compute it, and how even the EVM handles it, and how the dispatcher handles it. I'll end it here, but I really hope you learn more about the function selector, feel like you have a better grasp of it now. If you have any questions or comments, definitely let me know. Feel free to also, like and subscribe to this channel so that you can kind of follow on the latest new content as well. And I really did hope that you learned something. So thank you so much for watching. I really appreciate all the support. I'm getting so many helpful and useful comments. It really warms my heart, and I am going to continue making these videos. So thank you so much for watching, and I hope you have a great day.